Right. Our second speaker is Jacob Sprague from Northwestern University, and he will tell us about Superradiance searching for axion clouds with the levitated sensor detector. So let's welcome.
Hi, my name is Jacob. I'm a third-year grad student at Northwestern. I'm part of the LSD collaboration along with my advisor Shane and Andy, who just gave the talk on the instrument. And today I'm going to talk about one of the sources that we might be able to look for with this instrument, which is the axion cloud. So the axion cloud is essentially like a giant atom in space, where the nucleus is a spinning black hole, and the analog of the electron is this boson, except there's not just one particle, like in a hydrogen atom, but there's a whole bunch of them. So this phenomenon can occur not just at the microscopic level, at the quantum level, but this is actually a classical phenomenon, which is called superradiance, where a classical real scalar field near a spinning black hole can extract rotational energy from the black hole. The black hole spins down, and you get this exponentially growing macroscopic bound state of the scalar field, and eventually the cloud finishes growing, and the cloud is non-axisymmetric. It's oscillating, has a time-dependent quadrupole moment, and it emits gravitational waves. And over time, the cloud dissipates as it emits gravity waves off to infinity, and eventually it goes away, and you're just left with a black hole that may still be spinning, just not as fast as it was. So yeah, so formally, at the classical level, this scalar field, it obeys the equation that I have here, the Klein-Gordon equation. And in my work, I just consider the simplest possible scenario where you have a real electrically neutral scalar field, no self-interactions, just the simplest vanilla model of an axion cloud that you can have. And unlike the hydrogen atom, where you require the wave function to be regular at the origin, in this case, because you have a black hole, you require the field to be ingoing at the event horizon. And so the eigenfrequencies of these bound states are not guaranteed to be real. They are generally complex. And it turns out that the imaginary part will be positive if the real part of the frequency obeys a certain inequality for some integer m. And then omega sub h is the event horizon angular velocity. So as long as the real part is less than this m times omega h, then the imaginary part will be positive, and the amplitude of the scalar field grows exponentially. As it grows, the black hole spins down, so omega h gets smaller, and eventually the inequality saturates. This amplification, which is called superradiance, it stops, and that's when the cloud is finished growing. Once it's finished growing, it oscillates, emits gravitational waves. The frequency of the gravitational waves turns out to be basically it turns out to be exactly equal to 2 times omega r. So because high-frequency gravitational wave astronomy is still very much in its early stages, we're also asking, at the astro theory level, also very basic questions. Like, if there are these axion clouds within our galaxy, how many of them might there be? How many of them would be loud enough to be individually resolvable? And then for all the multitude which are not resolvable, what kind of confusion foreground do they present? Also, in order to be in the 10 kilohertz to a few hundred kilohertz band of the LSD, that corresponds to bosons, axions, in the mass range of 10 to the minus 11 electron volts up to a few times 10 to the minus 10. Yes?
So this effect clearly is there for black holes, but would it also exist for neutron stars, for instance?
No, it occurs for black holes for 2 reasons. One is because the Kerr black hole, the rotating black hole, is axisymmetric, and real neutron stars are not axisymmetric enough for this to happen. And the other reason is because a spinning black hole has a region called an ergosphere, or ergo region. It's basically if the black hole wasn't
Yeah, I know,
spinning. Oh yeah, yeah. So the ergo region, this superradiance phenomenon is very similar to the Penrose process. So with the Penrose process, a particle comes in, splits in two. One of them goes into the hole, and the other one emerges out of the ergosphere with more energy than the original incident particle. Superradiance is like the same thing, but for waves. So a wave comes in, splits in two. One goes in.
Yeah, I was just wondering because the Klein-Gordon equation that you started from would not be so different from in a neutron star gravitational field from a black hole gravitational field, right?
Yeah, but the neutron star doesn't have an ergo region.
Yeah.
So.
Okay.
So to model the population of axion clouds in our galaxy, there are two sides to the story. One is the dynamics of superradiance, and the other is we need to choose some fiducial model for the population of black holes in our galaxy. Now, our galaxy has lots of stars, and the stars are distributed roughly in three sections that we call the thin disk, the thick disk, and then the central bulge. And of course, our galaxy also has something called the dark matter halo. So we have two choices. We could choose to focus on primordial black holes, subsolar mass primordial black holes distributed out in the dark matter halo, or we could choose to focus on stellar origin black holes that occur within the thin disk, thick disk, and bulge. So I've chosen to just focus on the stellar origin black holes because at the very least, we know they exist. With the PBHs, we would have axions and PBH, two hypotheticals on top of each other. So I thought I'd focus on it, the stellar origin black hole population instead. So on the superradiance side of things, to simulate the population of axion clouds, for each black hole, you have to ask, given the mass and the spin of the black hole, which bound states of the scalar field can grow, how quickly do they grow, and then once they finish growing, how long does it take for them to dissipate? And then also you need to know what the gravitational wave frequency is that would be emitted from each cloud. And so like I said earlier, the gravitational wave frequency is proportional to the real part of the eigenfrequency, and then the rate at which the cloud... Oh, sorry, go ahead.
Sorry, just to make sure, this simple picture of states, it's because you're making some sort of quote-unquote non-relativistic approximation so that you can actually consider a stationary problem. Because in principle, this is time-dependent quantum mechanics, or is time-dependent perturbation theory, because there is the self-gravity of the black hole. And so these states would be kind of quasi-bound and change with time, right?
Yeah, so the non-relativistic limit, so this parameter here on the x-axis is the mass of the black hole times the mass of the boson with however many factors of g, h bar, and c to make it dimensionless. And it's actually the ratio of the, so g m over c squared has dimensions of length, and that's associated with the black hole. And then the mu over Planck's constant speed of light, that's the Compton wavelength of the boson. So this dimensionless parameter is really the ratio of the black hole size to the Compton wavelength. When that ratio is much less than 1, that corresponds to the non-relativistic limit. But in general, these axion clouds can have values of this parameter that are much larger than 1. The only trade-off, though, is that then the bound state integer, in this case, you see the n is equal to 8, which is a very high bound state. Yeah.
Right. So in principle, the approximation you're using is not valid for m mu equal 3, right? So I'm not saying, of course, maybe, I don't know how big of a correction this would be, but in principle, precisely in that limit, the approximation would fail, right?
So the Klein-Gordon equation, when you make this ansatz, without making any approximations, this ansatz separates the Klein-Gordon equation into an angular equation and a radial equation, like the hydrogen atom. And then you can solve them simultaneously using a numerical technique called the continued fraction method. So you don't actually, you have to make...
I understand the approximation. So I understand that once you make an assumption, whatever you derived is fully correct. I'm just saying that there are time-dependent corrections to that equation, especially in the limit for high. That's fine. Maybe it's a small correction. It's just to clarify the setup, I would say.
Yeah, but in computing the real and imaginary parts, no approximations were made at this stage. Yeah. Yes. So,
Sorry, could you remind me what X is here?
I'm sorry?
What X is here? Chi. Yeah.
Oh, Kai, this is the black hole spin.
Black hole spin. I
The
see.
dimensional spin. So basically, the angular momentum of the black hole divided by the mass squared of the black hole.
Okay. And what is the reason for having some cuts here? I mean.
Yeah,
so-
so if you choose a bound state, so here I chose the bound state where the in quantum mechanics, I think it's either called the radial quantum number or the principal quantum number. I can never remember which one it is. But once you choose, it's the one where, in quantum mechanics, you learn that the angular quantum number L can take values from 0 up to n minus 1. So that's what this n is. So I just picked n equals 8 and L and m both equal to 7 because the L and m equal to n minus 1, those bound states are the ones that grow the fastest. And then, so when you compute the real and imaginary parts of the eigenfrequency for different black hole spins, for the imaginary part, you can see them very clearly. You can see that these growth rates for the clouds can vary by many orders of magnitude. Whereas for the real part, it's actually very difficult to see the different spins. So the real part depends for a given black hole mass and a given boson mass, this real part depends only very weakly on the black hole spin. Now, this graph here of the omega I, which is the superradiance rate, I intentionally plotted this in a way which is dimensionless and scale-free. But if you choose a value for the mass of the boson, and then you take the reciprocal of the rate to get a time scale, then you get this more intuitive physical description of the growth time scale for the cloud as a function of a black hole mass. And then each of these sets of curves, in each set of curves, we've computed the timescales for various values of the black hole spin and done it for bound states 2 up to 8 with L and m both equal to n minus 1. And so you can see that the time that it takes clouds to grow can vary by many orders of magnitude depending on the black hole spin, the black hole mass. It also depends on which value you choose for the mass of the boson. So when we simulate the population of axion clouds in the galaxy, every time we do the simulation, we choose a value for the mass of the boson. And then we just,
So the black hole spin indicated here, that's the black hole spin at the beginning, when the cloud starts to grow, right?
Yes.
And then what stops the growth is that when the black hole has run out of spin, or
That's when the superradiance inequality.
when this equality is no longer satisfied. But at that time, roughly how much of its spin does the black hole retain at that point?
It's a good question. That I don't have a single answer for that. The amount of spin that it loses depends sensitively on things like which boson mass you choose.
But for instance, can that be an order 1 fraction of its spin, or is that much smaller?
Yes, order 1. Indeed, you can use, you can do a study of the different spins as a function of the mass.
Mm-hmm.
So it's called a Regge plane, function of mass with spin. And if you find black holes with sufficient spin, order 1, that means that there is no this process happening. So you can use the fact that black holes have a spin.
Yeah, that's what I was getting at.
Yeah. This
Okay.
is studied. Yeah.
Cool. Thanks.
I have another question. So how and when do you form these clouds around black holes? If black holes take billions of years to form, how quickly would you form the cloud?
Yeah, so the stellar origin black holes, they'll form when a star dies. So like when a massive star dies, it'll either just like directly collapse into a black hole with no supernova, or there might be a supernova and then there'll be a fallback onto the core, which then collapses. But in both cases, the black hole itself forms almost in an instant. And once the black hole forms, then if superradiance can happen, if there's a bound state which can grow, given the mass and spin of that black hole, it'll immediately start to grow.
Do you need a high density of axions around those black holes to form the
No,
cloud, or?
You can start even in vacuum, essentially, yeah. just due to usual like fluctuations. So now on the black hole, stellar origin black hole population side of things, we have to make some assumptions about the, if I pick a black hole in the galaxy at random, what's the probability of having a certain mass, a certain spin, a certain age? Here, when it comes to the mass distribution, I am going to intentionally choose a distribution which is very optimistic in terms of superradiance. Because again, going back to what I said earlier, we're asking very low-level questions. Questions like, what is the number of axion clouds we could expect? How many resolvable sources? But in fact, we also want to ask the question, what's the best possible scenario that we could get? The greatest number of resolvable sources. So in other words, what's the most optimistic scenario? So in the physics of star formation, the initial mass function for stars is defined in this particular way as some function that when you integrate it over some mass range tells you the total number of stars that are formed in that mass range. And then the usual form for the mass distribution that stellar astrophysicists use is called the Salpeter form, the mass to the minus 2.35, and then you have to normalize it on some interval. So I chose to normalize it on the interval from 1 solar mass up to 50 solar masses. And the reason I chose the lower bound to be 1 solar mass is because for the boson mass range relevant for the levitated sensor detector, a few times 10 to the minus 11 electron volts up to a few times 10 to the minus 10 electron volts, bosons in that range will, scalar fields in that range will experience superradiance optimally for subsolar mass black holes. But since I'm just considering stellar origin black holes, I set the lower limit at just 1 solar mass, which may not be very realistic because so far stellar origin black holes have not yet been found with masses of 1 or 2 solar masses, but they could be out there. They could be isolated rogue black holes, as astronomers like to call them, freely floating and like almost impossible to find. So just imagining, hopefully, that there are these isolated rogue one or 2 solar mass black holes out there. I've chosen this Salpeter optimistic form. We don't know what the underlying spin distribution of stellar origin black holes is, so I just took it to be uniform between 0.1 and 1. I could have done between 0 and 1, but I thought I'd start at a non-zero value to, since generically black holes do form with at least some spin, because the core of a star collapses, and collapse tends to spin things up. So the simulation itself basically means first you assign each black hole in the galaxy a mass, spin, and an age, and then you basically go through this little flowchart for each and every single black hole. You ask, given the initial parameters of the black hole, what is the fastest bound state that can grow? How long does it take to grow? If the time that it takes to grow is larger than the age of the black hole, then we just throw it out. We say the cloud is taking too long to grow, so it's not going to be astrophysically relevant. On the other hand, if the cloud does grow quickly enough, then we calculate how long it takes for the cloud to dissipate, and our measure of that is the time scale for the cloud to actually dissipate to half its initial mass. But regardless, we have to ask that question: is the cloud still radiating today, or has it dissipated? If it has dissipated, then we take the final parameters of the black hole, the final mass and spin, and we start over and we go through this again, and we keep going through this until either we find that from the birth of the black hole to the present, a cloud has formed and is still radiating today, or there are no clouds around that black hole. Yeah.
So if it takes a millisecond, like Deva was saying, then you would always replenish it.
Oh, sorry. It takes, and it's just like a millisecond instant once the black hole forms for the cloud to begin growing. So basically, the initiation of the growth of a cloud's growth begins as soon as the black hole is born. But the time that it takes for the cloud to grow is this represented, this plot I showed earlier, this one here. The time that it takes for the cloud to grow can be very long. It can range from years, hundreds of years,
So
billions
the
of years.
time for the cloud to grow takes billions of years,
Yeah,
not milliseconds.
correct. Yeah.
Right.
And it could take billions of years, hundreds of millions of years, 1 year. There's a range of possibilities. Yeah.
Sorry, I didn't quite understand this cycle of a cloud grows, a cloud dissipates, a cloud grows again. Wouldn't you rather reach some sort of equilibrium where production and loss balance each other and the cloud just reaches some sort of steady state?
No, so once a cloud grows, it inevitably dissipates because it's emitting gravitational waves.
But then wouldn't you immediately replenish the particles that are lost that way, or the energy that is lost that way?
No, because the cloud that grows is a particular bound state of the scalar field, which satisfied the superradiance condition with the initial mass and spin of the black hole. Once that cloud has grown, the mass and spin of the black hole have changed to some lower values. That cloud dissipates, and now a new cloud can grow, but it will be a different bound state. It will be a higher bound state. So if the first cloud that grew was the n equals 3 bound state, once it disappears, once it grows and then dissipates away, the next one that grows might be n equals 4, n equals 5.
But can't that happen concurrently, that the growth of the next one starts while the former one is still in the process of dissipating?
Yes, it can. And I'm intentionally ignoring that complication.
And in a similar direction, what takes longer, growth or a dissipation?
The dissipation, I wish I had a plot of that on here, but dissipation timescales can be several orders of magnitude longer than the age of the universe. So it takes much longer for it to dissipate.
Okay, so that means in this procedure that you're following here, it's very unlikely that you happen to have a black hole that has gone through several cycles already, but at the present day, it's just at the time where it's growing, and then you would throw it out because of this condition that if the time it takes the cloud to grow is less than the remaining time to today, then you discard that black hole. So that's unlikely because it takes much longer to dissipate than to grow.
Yeah.
Okay, thanks.
So with this stimulation procedure in mind, so the next few slides, I'm just going to show you some of the results of one of these simulations where I've taken the mass of the scalar to be 3 times 10 to the minus 11 electron volts, which is on the low end of the LSD band. I think around like 14 kilohertz for the gravitational wave frequency. So this left plot shows the gravitational wave frequency of each and every cloud that has, so by the way, the number of stellar origin black holes in our galaxy is estimated, astronomers estimated order of magnitude to be around 10 to the 8, 100 million. In doing these simulations, I, for the sake of the simulation not taking forever on my laptop, I use 1 or 2 million black holes. And then out of those 1 or 2 million black holes, the number of axion clouds that results from the simulation is usually on the order of, at most, maybe 200,000. In this case, for this 3 times 10 to the minus 11 boson, the number of axion clouds that are still present today is something like 200,000. And as you increase the mass of the boson, do the simulation again for larger boson masses, the number of extant clouds gets smaller. So 100,000, 50,000, it gets smaller. But the ones that are still around today, you see that the gravitational wave frequencies, as a function of the black hole mass, they follow these sloping downward curves, which is the same as what I showed you earlier when I showed in the abstract the real part of the eigenfrequency as a function of that dimensionless product of the mass of the boson and the mass of the black hole. So you see that expectation is borne out. Likewise, with these cloud growth times, they follow this sloping downward shape as well. And the fact that each of them has a thickness like this has to do with the fact that the black hole, these correspond to black holes of different spin, and in particular spins that increase going to the right. Now you might wonder, these axion clouds, how massive are they? So if the mass of the black hole is, anywhere between 1 and 50 solar masses, how much mass can you get out of these black holes? And you find generally that these axion clouds have very little mass. So if you might remember, back in 2015 when gravitational waves were detected for the first time, GW 150914, you heard that you get two black holes of like 30 and 35 or 29 and 36 solar masses that merged. You'd expect that the final black hole would have 65 solar masses, but actually it didn't. It only had like 62 solar masses because 3 solar masses worth were turned into a big burst of gravitational waves. Axion clouds are like the complete opposite end of this idea of converting mass into gravitational wave energy. Here you have, anywhere from 10 to the minus 3 solar masses up to at most half a solar mass converted into gravitational waves, but occurring, as I said earlier, over an extremely long dissipation timescale. So very little mass being converted into gravitational waves over a very long timescale. So as you might expect, then that the gravitational wave amplitude is going to be very, very small. You expect these to be very weak signals. And indeed they are. So if you then plot the dimensionless, so these are continuous sinusoidal waves, these gravitational waves. So they have an amplitude and they have a frequency. So I just plotted the amplitude versus the frequency, and you see that generally these are extremely weak sources, and you don't expect that we're going to be able to see the great majority of them. Now, so in Andy's talk, he showed this plot of the projected strain sensitivity for the 1 meter, 10 meter, and 100 meter versions of the LSD. So taking these sensitivity curves, you can calculate some nominal value for the signal-to-noise ratio in a coherent search, where basically the SNR builds up with the observation time. So I took the observation time to be a million seconds. And so that same plot that I just showed, which just had the dimensionless strain amplitude, all I've done is just multiply by the square root of T obs divided by the sensitivity curve. And I'm showing for the 1 meter instrument, the prototype that's currently being developed, and then this 100 meter concept. And if you
can you quickly go back to the previous slide? In that plot, superradiance 1 solar mass, is that 1 solar mass black hole at 10 kiloparsec?
Yeah, 1 solar mass black
So
hole.
that's the mass of the black hole, not of the cloud.
Yes.
Okay, but it's still for a single black hole, so you're not taking into account the fact that you're going to have a stochastic signal from the integrated 100 million black holes, because that should be much larger, right? That's what you would see first.
Yeah. So actually, in the summary slide, I'm basically going to say that we haven't yet figured out how. Me and my advisor Shane haven't figured out how we're going to deal with that confusion foreground yet.
Mm-hmm. But that's a discovery as well.
Yeah, it is. Yeah, and I'll come back to that.
Okay.
At the end. Yes.
Thanks.
Mm-hmm. So then you could, if you set some nominal threshold on the SNR for saying whether the source is resolvable or not, then you can then just count how many of these sources have SNRs above that threshold. So I took the threshold to be 5, and in doing so, find that with the 1 meter and the 10 meter instruments, there are no resolvable sources, but with the 100 meter instrument, there could be some resolvable sources. Now in this plot, so last 2 plots I've been just talking about a simulation where the boson mass is 3 times 10 to the minus 11. So if you then count the number of resolvable sources with the 100 meter LSD, you get these are the SNRs from that simulation that I've just been talking about for the last few minutes. And then if you do the simulation again for more values of the boson mass, then you get this plot. So if the boson mass was, say, 5 times 10 to the minus 11, you see that there are a whole bunch of axion clouds with SNRs greater than that threshold. And if you then count up the numbers of resolvable sources, you find that the numbers are on the order of maybe a few hundred, and as you get to higher boson masses, the number dwindles down to 100, and then a few tens, and then just a few at masses close to 2 times 10 to the minus 10 electron volts. So I'll just go ahead and summarize then. So as we just said, the 100-meter instrument could see, depending on what if there is an ultralight scalar field out there in nature, and if its mass is less than about 2 times 10 to the minus electron volts, then the 100-meter instrument could see maybe anywhere between order 10 to maybe upwards of 1,000 resolvable signals. In this optimistic scenario where we've taken the black hole mass distribution to be this, Salpeter power law, and also the fact that in calculating these SNRs, we have not taken into account the confusion foreground, which basically acts as a source of more noise, which would decrease the number of resolvable signals if we took it into account. But this confusion foreground, even though we haven't yet decided exactly how we're going to go about computing it, we can, because there are so many of these extremely weak axion clouds, we can, maybe there's not much at this point. There's not much. How should we say? Substance. What I'm about to say, but maybe this foreground could be detectable by the 1 in 10 meter instruments, even if those instruments can't see resolvable signals. That's just a hope and a prayer at this point. But with that, I'll go ahead and conclude. Thank you.
Very interesting. So if black holes are dressed by these axion clouds, shouldn't we see this in LBK?
And what?
The usual mergers of black holes. They should have some signature as these two black holes in spiral in and merge.
Oh, LVK. I see.
LBK.
Yes, so I do know that there has been an all-sky search for continuous waves from axion clouds, and
I'm not talking about continuous waves. I'm talking about mergers of black holes. If they have clouds around them, and their masses, you were telling me the size of the cloud is about several times the shorter radii, and therefore you should see this in the final merger.
Oh, I see.
I can answer.
Yeah, so I do not know the answer to that.
But there have already been papers. So Richard Brito has several papers where. So it depends on the mass of the axion, right? So we have already excluded several ranges of the axion mass range, just because at the end of our mergers we don't see these signals. So that's
how many
correct.
of those mass ranges?
I don't know.
Lighter axions because LIGO is in the audio band.
Yeah, LVK. So LIGO would be like 10 to the minus 13 electron volt bosons.
And also, you need highly spinning black holes. And also, when they are in binaries, it's not clear if the cloud is disrupted. So all this is for isolated black holes. So this is still a big. This is an interesting question to understand what happens when you have these clouds in a molecule. Let's say.
Yeah.
In a binary.
Yeah, but it's called a molecule now.
Thank you. The mass range for the action is very limited, and also it's not optimal for the experiment. Is there any other motivation why to search for that range? I mean, some theoretical argument why that mass range is special?
Not that I'm aware of. Our main motivation for doing this is just to
Because the experiment is
just to rule it out if we can.
right. Okay.
I mean, it is the gut scale axion mass, right?
Yeah, so FA at the gut scale gives you
Yeah.
the frequency. Yeah.
Okay. So that's okay, thank you.
Yeah.
Does accretion onto black holes play any role there? Because an accretion disk can spin up a black hole again.
Yes.
I guess integrated over the population is probably not a super important effect, but I was wondering.
Yes, it can. It can spin up the black hole, and it could maybe disrupt the growth of an axion cloud, but we haven't accounted
Yeah.
for those kinds of things.
Yeah, I didn't want to interrupt you before, but before you were asked about the neutron stars.
Mm-hmm.
So neutron stars can superradiate, indeed. You don't need an ergosphere. The only thing you need is something that rotates very fast, which is hard because neutron stars rotate typically slower than black holes, which are extremal. And also you need something that dissipates. In the ergo region, you dissipate very efficiently. And a neutron star, they are very small, so in principle, they take a hard time. I mean, it's much harder for neutron stars to produce superradiance. But in principle, for instance, even a disk that conducts and rotates can superradiate.
So you're saying a neutron star doesn't dissipate its spin as efficiently because it's still a bit larger. It's still a bit larger. You don't.
No, but also the event horizon or even the ergosphere is a region that really dissipates very efficiently. You compute the conductivity or whatever. Where as compared to a black hole, a neutron star, the black hole is way more efficient in this. But in principle, as I said, a cylinder that rotates will also superradiate if it rotates very fast. It has never been observed in the lab. It has also only been observed with some analog superradiant rotation in fluids. But as I said, Seldovich was the first person who understood this, and it was with a cylinder that rotates.
Mm-hmm. Yeah. Thanks.
No worries.
But for neutron stars, shouldn't we have some post-Keplerian constraints from binary pulsars? You should see the cloud, no? Because one of the pulsars is pointing towards you across the field of the other one.
In standard neutron stars, it doesn't happen.
Not standard. Binary ones where there's one that crosses the cloud.
In the standard model, you need the action to really couple very strongly to the neutron star to dissipate efficiently. And these models are so-so. There are papers on this. I can point you to them,
Yeah, maybe you said this already, but how is your sensitivity to stochastic signals? So you said in the end you had a statement about the non-resolvable signal.
Yeah, so at the bottom when it says the foreground could be detected by the 1 centimeter instrument, I said that was just a hope and a prayer. I'm just saying that as a maybe, but we don't actually know how to. At least I don't know how to compute this background yet. So.
Okay.
So in your plots, you consider the m times mu to be like order 1, right? I mean, in early plots.
Of the in mu, yeah.
Yeah, to be order 1. So I thought it sets the, ranges of mu, which is axion mass, right?
Mm-hmm.
So once you determine the mass of the black hole, which is large m, then it should be along the inverse of m, right? No? You consider only m times mu to be order 1, and once you fix the mass of the black hole, it sets the possible ranges of axion mass you can.
Oh yeah, so in our simulations, we don't set the mass of the black hole. We set the mass of the boson to some value, and then we assign each black hole in the galaxy its own mass, and then determine on a case-by-case basis the bound states and axion clouds that would grow around each one.
Mm-hmm. Oh, I see. So, and relating to this, even if you only consider the larger solar mass, mass larger than solar mass black holes, but what if you just extrapolate your regions for smaller mass regions? What do you expect? Because smaller mass shows a better kind of prospects.
So if we had done this, instead of the stellar origin black holes within the disk and bulge of the galaxy, if we had chosen to consider the dark matter halo of the galaxy and said that the dark matter halo has some fraction of it consists of subsolar mass primordial black holes, then in that scenario, with the same axion mass range that we've been talking about here, 10 to the minus 11 electron volts, then this dimensionless parameter would be much smaller than 1. And superradiance would be, the conditions for superradiance would be optimal. The trade-off, though, is that because the PBHs are, subsolar mass, so with these massive black holes, these 1, 5, 10, 20 solar mass black holes, we found that cloud masses are extremely small, and gravitational wave amplitudes are extremely small. If we had done this with the PVHs themselves are sub-solar mass, and so the axion clouds that form around them would be even tinier still, and the amplitudes would be even tinier still. And also, the dark matter halos, what would be the number, like, several tens of kiloparsecs extended beyond our galaxy. So sources that are far away are just inherently weaker because they're so far away. So that's also another reason why we chose to stick with the stellar origin black holes, is because we know that they exist and they're in the main baryonic section of the galaxy, so they're closer, which helps in terms of the distance issue.
So I have a question about the directionality of your search. So you were quoting a signal-to-noise ratio, right? But if you're targeting the galaxy center, in principle, you can fix the sky position or target a certain range of sky positions, and that should increase your SNR. So are you doing something like that? Or?
I'm not, no.
Okay.
I'm not, but there are people who are. And I was just, the other day I was reading about a technique, which I can't explain because I don't understand it yet. But it's called hidden Markov model tracking. It's some technique for doing directed searches. So
for continuous waves in LBK, right?
yeah.
Yeah. Okay. And if I can, another brief question is, so you're assuming that this action only couples to the gravity sector, but in principle it could couple either to a dark photon or even to standard model photon, and that would significantly change. So first there could be no linear interaction, but even without no linear interaction, it could significantly alter the signal, right? So in principle, these are optimistic bounds because you're killing other channels, right?
Yeah.
Okay.
Yeah. Everything we've done here is as optimistic as possible. Although there is another scenario of a certain optimistic scenario where these bosons, these scalar bosons, have self-interactions. They couple to itself. And that can cause, as the axion cloud grows, it can cause the cloud to become unstable. And instead of dissipating over a long time scale, the cloud suddenly just like explodes, so to speak. It's like all the bosons suddenly annihilate and produce this thing called a bosnova. That's another scenario that some people have considered. Leads to a transient gravitational wave burst rather than the continuous. There's a question over here.
Yeah, it's actually a question for Andrew. Because you mentioned, okay, kind of the main effect was the gravitational wave force on the mirrors of the cavity. Now, I mean, in principle, there's also, of course, a gravitational wave force directly acting on your little particle. Is it obvious that that's irrelevant?
Well, so if you try to look for the deformation of the particle itself, of course, that's nearly impossible because it's a sub-micron thickness, right? But
the wobbling of it.
Yeah, but the wobbling of its position is important. But the way, so it's kind of a subtle calculation. So it turns out that you have the maximum sensitivity if the particle is near the input mirror of the cavity, and then in this case the differential strain taking the input mirror as the reference. So the position of the particle doesn't move very much, but the end mirror essentially moves the most in that frame. If you were to put the particle on the opposite end of the cavity, actually the effect goes away. So there's no effect at all. And this is something that
it has to be symmetric, right? Why is that not symmetric?
The symmetry is broken by the direction the laser hits the cavity. So we actually got that wrong, and the referee actually corrected us, and then we checked it in 2 gauges to verify they were right. but yeah, so it's a little bit, you have to be a little careful about what frame you use and that sort of thing. But it turns out that you can think about, at least in that frame where you think about the reference point as the input mirror, that most of the effect is coming from how the end mirror is moving around.
Also, you want your particle trapped in a relatively steep potential, right? You want a rather intense laser to trap it steeply, and that probably diminishes the response of the individual particle, because it would mean that the particle would need to move relative to this relatively steep potential, right? Or am I getting this wrong?
Well, so the steepness, it basically determines the trapping frequency, right? So if you want to look for higher frequency waves and look for resonant excitation, you want a higher intensity trap or a bigger gradient in the laser intensity along the beam. But so the mirror the motion of the mirror essentially just displaces where the trapping minimum is relative to the particle, right? And so, it's really so your adjustment of the laser intensity is essentially just changing the frequency that you're sensitive to by moving the resonance around.
Okay.
Right. This is Q&A session, so you can have questions to Andrew too. By the way, Jacob, I have a quick question. So black hole should have a high spin for superradiance, right? And LBK has measured the black hole spins, and most of them have a small spin. So does it have some implication on the superradiance rate or whatever?
Yeah, so superradiance can happen even for small spins. It's just that the bound state that can grow. So so for small spins, you need higher bound states. That's why we've computed these superradiance rates and so forth for bound states ranging from n equals 2 all the way up to n equal 11, was to take into account the possibility that a stellar mass black hole could experience superradiance even if it had a low spin.
Okay, thank you.
Along that direction, so we were mentioning before binaries, how difficult it is to model these clouds in binaries.
Oh, how difficult is it?
Has anybody tried?
Yes. Yes, there is a paper that I once saw. I want to say it was by Daniel Bowman and John Stout and a few others that was on the issue of superradiance in a black hole binary and how with the orbital frequency matches. So in principle, there's another way for axion clouds to emit gravitational waves. There are two ways. One is the way that we have it here, where we have a single bound state, which oscillates and emits gravitational waves. The other possibility, if you think of this at the particle physics level, what we've done is we considered just this scenario where like two bosons annihilate to a graviton. Another possibility is that you have a boson in one energy state, and it transitions downward to a lower energy state, and emits a graviton in that process. And if you have two black holes in a binary, and one of the black holes, or maybe both of the let's just say one of the black holes has an axion cloud in some bound state, it's possible that if the orbital frequency matches the frequency corresponding to the energy difference between the bound state, which is actually present, and some lower bound state, it can cause the cloud to transition from whatever bound state it's currently in to a lower bound state and emit gravitational waves in that process.
It could be that just simply the gravitational wave emission from the binary would disrupt the cloud. It just simply excite the cloud and disrupt it. The two black holes orbiting each other, remember that the frequency is similar to the period, and that's similar to the size. And therefore, when they are near each other, and therefore these gravitational waves could just simply disrupt the cloud.
Yeah, so that's essentially what happens. The cloud isn't disrupted, it's just it's
excited to higher levels.
Yeah, the perturbation due to the orbital frequency causes the cloud to transition from say n equals 3 state down to the n equals 2 state or something like that. So it causes that sudden transition downward, which causes gravitational wave emission so in that case there would be two types of gravitational wave emission, one from the orbital motion of the binary, the in-spiral, and the other from this axion cloud around one of the black holes that suddenly transitions to a lower state.
Rather than lower, thinking of higher. So you excite the level of the axion cloud rather than de-excite it. By emitting gravitational wave, you absorb the gravitational wave from the binary.
Oh, you're asking, can an axion cloud absorb it from the binary? That's an interesting question. I don't know the answer to that. That's interesting. Yeah, I mean, perhaps. I'm not sure.
Yeah, sorry. There have been simulations by Bertie's group, and it's very complicated because there are many time scales, many resonances. Yeah. So I think that they don't still know the answer. So the paper you were mentioning is analytic, one by Baumann et al. But certainly there are many things that are not so trivial, and they're trying to solve it with simulations, but it's quite hard, I think.
No, but also, sorry, you have to distinguish. So I think you're referring more to the comparable mass case, right, where it's much easier to disrupt the cloud. I think the group of Baumann is focusing a lot on the extreme mass ratio in spiral cases for LISA, and in that case, it's easier to not disrupt the cloud.
Yeah, the other thing that Bowman's group has worked on is the ionization of an axion cloud, in which the axion cloud itself, it doesn't produce, instead of producing gravitational waves, the axion cloud itself gets ejected from the black hole. And so all these bosons, so instead of gravitational waves, you have scalar waves that get emitted. But we're not trying to detect scalar waves, so I was not consider that.
Any other questions? Right, then maybe last one.
Yeah, it's a curiosity for Andrew. So, do you also study rotation, or you can also spin, I guess, your stuff, right? But is
at the moment, we're just trying to damp out the rotation. We tried to just focus on the motion along the cavity arm. But in principle, maybe you could do something we haven't really thought much about.
All right, let's thank Jacob and Andrew again.